In this video, we're going to look at an exponential function, the form of an exponential function, and hopefully solidify some of the things that you've already been thinking about. So an exponential function grows or decays by the same relative amount per unit of time for any quantity q growing exponentially with a fractional growth rate r. So when it's talking about a fractional growth rate, usually this is presented to us in the form of a percent. For example, if we have a growth rate of 5%, let's try this again, a growth rate of 5%, then we would put 1.05 right here for our growth factor. Okay, if it's decaying, then we would put that as a negative. So, this is a little tricky, the notation here. You might put, some books might show plus or minus. So if it's an increase, you add that rate. If it's decreasing, you would minus that rate. Or you could think of, if it's decreasing by a certain percent, then you would put that in your equation as negative r. So let's look at some of these other values. So Q is the value of the exponential growth quantity at time t. That's your output. Q0 is the initial value of the quantity, and we usually know this. R, again, is the fractional growth rate, or a percent growth rate, fractional or percent. Let's put that here. Most of the time it's presented as a percent, but you could say you lost 1/3 of your value, or you could say you gain 1/4 of your value. That would be the same as gaining 25%. And t is time. So here it's telling negative values of r correspond to exponential decay. That's kind of what I was talking about over here. One thing to be aware of is that the units of time used for t and r must be the same. So if I say that this r is decreasing by a certain amount per year, then this time has to be in years. If I say this is decreasing at a certain amount per month, then this time has to be in months. There's ways to modify that and deal with that, and we'll look at some other examples there. That's an important thing to understand. Okay, so I want to write this out a little bit different here. I want to write this as Q equals, and then use some colors. This is a number we're probably going to know, the initial amount. And then we're going to have the parenthesis and the 1 and the plus are always going to be part of the formula. The rate is going to be something we're probably going to know. And the time is going to be the input. So when we're thinking about this graphically, we would have the time on the x-axis and the output, the value of the exponential quantity, on the y-axis. And these would all be numbers that we would probably know and be able to plug in. Let's look at an example. China's rapid economic development has led to an exponentially growing demand for energy, and China generates more than 2/3 of its energy by burning coal. During the period from 1998 to 2008, China's coal consumption increased at an average rate of 8% per year. And the 2008 consumption was about 2.1 billion tons of coal. Use these data to predict China's coal consumption in 2028. All right, so let's think about our formula. We've got Q equals Q sub 0 times 1 plus R to the T. So remember, Q sub 0, that's your initial amount at time 0. Did we write that over here? That would be a good thing. Oh, here we go. At time equals 0. So when you have a real life problem like this, you have to decide, when is time 0? So our input is going to be T and our output is going to be Q. Remember from before? Input T, output Q. So what year is going to be time 0? Oh, let's go back over here. What year do you want to be time 0? Well, we know that in 2008, the consumption was 21 billion tons of coal. So if we make 2008 times 0, then we know our Q0 is going to be 2.1 billion tons of coal. And we need that number. So I would say let times 0, I didn't leave myself a lot of space here, refer to 2008, and so then the output is $2.1 billion tons, and that's also your Q sub 0 number. So we have 2.1, and that's in billions, so we could specify that this Q is in billions, times 1 plus R to the T. Now, what is our R value? What is happening to this coal? Well, it says that it's increasing at an average rate of 8% per year. So since it's increasing, we're going to add 8% or 0.08. So the amount of tons of coal consumption is going to equal 2.1 times 1, that's a parenthesis, let's make that a little more curvy, 1.08 to the T, where T is the number of years after 2008. T equals number years after 2008. Now, what if we made T equal to 1998? Well, then we wouldn't know what Q sub 0 is, because Q sub 0 stands for the whatever the output is in time 0. And we didn't know what the output was in 1998. We would have had to work backwards 8%. That would have been a whole nother problem in and of itself. That would have taken a lot of time to figure out. So whatever your initial value is, it should be something that you know, and then if you know that year, you make that your T equal 0 year. Okay, now they want us to use the data to predict China's coal consumption in 2028. So 2028. What T value is that going to be? Well, T is the number of years after 2008. So 2028 has a T value of 20, right? Because it's 20 years after 2008. So if I want to know what this output is, it's going to be 2.1 billion tons of coal times 1.08 to the 20th power. Because we're increasing by 8%, 8%, 8% every year for 20 years. So we have to multiply by 108% 20 times, or 108% to the 20th power. All right, let's get out our calculators and see what this is. 2.1 times 1.08 to the 20th power. I get 9 point, I don't know where we're supposed to round here. Let's see, 9.788. Let's do that. 9.788 didn't tell us where to round. And that would be billion tons. So if we wanted to write this out the long way, let's see, we'd have to go 1,000, million, billion. So 9.788 billion tons is 9,788,000,000 tons of coal consumption. All right, so I hope that helps. It helps you figure out how to write an equation for exponential modeling. What you're really looking for here is you're looking for the rate and the initial value. So one thing to be aware of with exponential growth and decay and how it's different than linear growth and decay is, as in exponential growth, if you pick some point on this graph, you can look at the slope of the line that's just touching that graph. And as the x value increases, these slopes get more and more and more positive. That's like that exponential growth, right? It just starts to blow up after a certain amount of time. Exponential decay, the slope starts steep, and then it gets less and less and less as we come down here. And you think about how that's different than linear growth. With linear growth, if I had a linear growth, I don't want to use that big fat line. Let's use a different line. If you had linear growth, that slope stays constant no matter what point you pick. It's growing at the same rate. Same thing with linear decay. All right, hope that helps. And just remember this form of exponential equation, and that will help you on a lot of these problems.